We're good? Sweet, can they hear me? All right, cool. Hey everyone, welcome. Welcome back to COMP1511. You may be thinking, hang on a second, that's not Sophia. We're back to Henry. Yep, I'm back. This is the last lecture. Jake returns from Italy, I believe, sometime today, and then has decided to give the lecture tomorrow, despite there being, I think, a 10-hour time zone difference. So good on Jake. But until then, you've got me for one more lecture. So I've got a few announcements I've been asked to make. One of them is that online students, and I'm pointing to the people on the camera right now, so presumably you're those students. Please sign up for an in-person TLB week 10, because that means you can practice the final exam. If you are in an online tutorial, sign up for an in-person one. This is because you will gain experience in the practice environment. Has anyone here had a chance to play around in the exam environment yet? Yep. Was it the exact same as programming at home? No. It is a different experience. It is an experience you don't want your first one to be when everything's on the line. You probably want it to be after you've had some time to practice what's happening. So please make use of this chance to practice in that final exam format, because then you'll be entering it feeling much better prepared. People may have questions for me just about the exam in general. I will preface by saying I know nothing about the exam. I don't actually know much about the exam except that it's 3 hours long and there will be 2 sessions and it's like sometime in the future, I think. Or it's right now. No, that's unlikely. Sign up here for those in-person practice exam things. There's a code to access it, but because these lecture slides are available online, you can also just look at it and that'll be fine. So yep, make sure if you're an online person that you sign up to have a chance to practice. And if you can't make it in person, you can watch this video here, which does outline what it's like and walks you through it. But you should really just go in person anyway. Hello. Technical difficulty? Is it the mic?
It's the string.
Okay, yep. Parkour.
Sorry.
You're all good.
Do you mind just sending me this? Actually, fuck, I
Just having some small technical difficulties, but until then, make sure that you've signed up for one of these. If only I'd generated a QR code, that would have made our lives so much easier.
Wait, so is that the access code?
The access code, oh no, that's the YouTube video, whoops. The access code is COMP1511 though.
Okay.
Oh, recursion.
You can do recursion today.
I wish. Maybe I will. You can't stop me.
Do you mind just sending me that? Do you have Teams open, or if it's not?
Yeah, just type Teams in the top.
Thank you. Is this okay?
Yep.
Just stop me if anything.
Wait, Comp 1511.
Yeah, that's the access code.
Any caps?
All caps.
All caps.
All caps.
Teams. Okay. Fingers crossed. I'm really sorry about this.
No, it's all good.
Microphone freeze.
Yeah. So yeah, if you're wondering about the access code, it is COMP1511, and it's there. All right, we're back from technical difficulties, which means we're back to the lecture, which means we're for more announcements. MyExperience, I don't entirely know what MyExperience is, but I've deduced from the name that you can tell us about your experience in the course using MyExperience. There is a lot of feedback you give to us for COMP1511. The MyExperience feedback is the most important feedback you can give us. It really shapes how this course is in the future, and so we please beg of you, we implore you, we really, really, really want you to fill out the MyExperience form and just tell us what you thought of the course. We take a lot of the feedback on board. We're constantly making changes to the course based on the feedback you give, so please do it. COMP1511 requires a lot of resources. We've got the YouTube live stream, we've got our whole team of moderators here, we've got our tutors. We do a lot to take care of over 1,000 students every instance, and so any feedback would be greatly appreciated. If you want more courses like this course, tell us. Put it in the form. Say that you liked it. Say what you didn't like. Say what we can improve. It is completely anonymous. There's no way for us to track who's who unless for some reason you gave us your full name and your student ID number, in which case we could probably figure it out from there. But I highly recommend you don't do that, assuming you want to remain anonymous. And it is run by UNSW at large. So it's not run by an individual school or the faculty. It is run by UNSW. Now there are some, I don't actually know what these numbers mean. What does greater than 70% mean in a MyExperience report? They don't know. What does it mean to be?
Like more than 70% of the students responded.
Oh, okay. So this isn't even like greater than 70% approval. We just want greater than 70% respondents. If greater than 70% of you respond to MyExperience, there will be a bonus Jake plus tutors Q&A chill live stream games. I think at some point Jake was talking about ripping some Pokemon TCG packs on live stream. Chasing after that holo Charizard, you know, seeing what we can get. I actually wasn't invited, but I might show up anyway if we get above 70%. So this is a recommendation. This is a bonus. If we get greater than 80% of people filling out MyExperience, we don't know what we're going to do. We have no idea what's going to happen if greater than 80% of people fill it out because it's never happened before, and we're not entirely sure that we can actually count that high. Maybe the system just caps out at 79%. We're not sure. We'd love to see it, and I'm sure something big will happen if it happens. Like I'm doing a stand-up comedy show in a few weeks' time, and I said to Jake that if we get more than like 80-something%, I'll let the class write one of the jokes that I'll say, but that seems really dangerous, but I'm pretty safe saying it because it's not going to happen. So prove me wrong if you want to embarrass me in front of all of my friends and family. Right, this time I did do a QR code, so I'm going to give everyone like a few minutes to scan this and complete it if you want to get those bonuses. And there's a link there as well. While you scan and complete it, I'm going to crack open my Coke Zero. Have you all given up? No. Okay. I just thought you were leaving. It's like I'm out. Yeah, fair enough. All right. Please do fill this out at some point, and that sums it up. I don't know how long the form is. Is the form like super long? Do we need a few more minutes? How long is the MyExperience form?
It's annoying to click through stuff, but it can take a little bit of time.
All right. I'll give them a few more minutes then. Mainly because I really need to pad this lecture. I'm just kidding. I'm super prepared. Yeah. How's chat looking?
A couple of questions about like attending in-person practices.
All right, cool. Those are great questions. I know nothing about them.
I think Brenna's mostly answered them. So
Perfect. If anyone's watching at home, this is the part of the lecture that you can skip through. assuming you're watching it after it's been live streamed. There will be no nuggets of wisdom dropped within the next 2 minutes. It changes. Astro's Arcade is quite a good one. The Laughing. The one that's coming up is a tech versus biology debate, where which science will save the world. I'm on team tech for some reason. They wouldn't let me on team biology. And so I will send a link to that. No, I won't. But you can find it, I'm sure. All right. I accidentally clicked the next slide button, so I guess we're moving on to the next slide now. The assignment. Who here is like feeling good about it? 2 thumbs up. We're feeling happy. Is anyone here feeling like anxious about it? Yeah, no, that's fair. Anyone here feeling like sad about it? Yeah. Anyone like feeling hungry about it? Just going through all the human emotions that I know. Yeah, like it does take a lot of time and it is a lot of effort, and I do understand that. How are people progressing so far? Have people finished stage 1? Yeah, that's good. That's a good start. Are people on to like stage 3-ish, roughly? Yeah, nice. I don't actually know. Where do we expect the students to be up to in the assignment right now? What's a good place for them to be?
Like 6 hours is the bit.
Like if you've got through stage 1, you're good.
Okay, if you've got through stage 1, you're doing well. And how are they doing if they've got through stage 2? Better? Pretty good? Nice. If you've finished stage 1, you're doing great, keep it up. And if you're on stage 2, getting through it, you're doing well as well. And if you're past stage 2, then you're just doing great. So keep on smashing it. But one thing, I rewatched a few of the lectures from the previous years and the previous terms to figure out what to say. And one thing Sasha hammered home is please take care of yourself when doing these assignments. I know we're all programmers here, and it can be tempting to just stay up until 4 a.m. grinding out the code, grinding out the problem. But it's really not that healthy. You do still need to like eat and drink and sleep and all that good stuff. So just some reminders, like sleep is still important, food is still important, going outside and touching some grass is still important, and watching episodes of Australian Survivor is still important. And if you've not done that, I highly recommend watching Titans vs. Rebels episode 18. It's called the Best Actor Award. It's like one of the best episodes of the show. But other than that, just as long as you're doing these 4 things, as well as your assignment, then you're probably having a pretty balanced time. Right, that's all the announcements. Oh no, another one. If there is a lot of confusion about linked lists, then Jake made this video a few years ago. He calls it an intro to assignment 2. So I assume if you're done with stage 1, you might not need the video, but if you are feeling a bit stuck, this video by Jake is a great one. It really clearly explains linked lists. So I recommend giving that a watch. All right, now today I'm doing what I refer to as linked list leak code, but they're not actually leak code problems because I can't afford to pay for a leak code subscription. But these are just sort of small programming problems that I imagine might come up in an exam-like scenario, with the caveat being, I've not read the exam, I don't know what's in it, but I imagine they're more likely to be small sort of linked list problems as opposed to big things like the assignment. So we're going to go over some sort of things I can expect in linked lists. If time permits, we'll continue doing the Spotify thing from on Tuesday. Sophia did a great job with that one. That was a brilliant introduction to the assignment and an introduction to how to work with two-dimensional linked lists. But if we don't get time for it, I would like to point out that Sophia did fill in all of the code that she didn't get to completing on Tuesday. And studying code is a highly underrated skill. So if we don't get to continuing the Spotify thing, please do go through the rest of Week 8 Lecture 2 code, read through it, understand what Sophia's done, understand why she's done it, and that will improve your skills as a programmer. And if you have a friend you could do it with, that'd be even better, because then you're doing peer instruction and it becomes an even more effective study method. And so yes, that's why we'll do it later if time permits. All right, who wants to link some lists? Yeah, go on. Get into it. Get after it. Right, I know I'm sharing my screen. I guess I'll minimize that. This is still up on the live stream. We're still good. Cool. So on Monday, last time. All right. Let's quickly recap what a linked list is. What is a linked list made of? A linked list is made of a struct. What is the struct? What type of struct is it? What do we normally call the struct? Yep. So it is a node. And what does the node contain? It contains some data and a pointer to the next node. So we'll have a struct. Oh, brand new whiteboard marker. It will contain some sort of data in it. And it will contain a pointer that says, here's the next one. And this is great compared to arrays because it means the memory that we're using doesn't have to be contiguous. We can just put the memory on the heap and point to it. Go to the next one. Until eventually, what happens when we get to the end of the linked list? How do we know that we're at the end? Yeah, we're going to point to null. And because all of these are allocated on the heap, what do we need to do to all of them once our program's done with it? We need to free it. Cool. So we've got the basics of linked lists. They sound pretty sorted to, oh no. Oh no. Oh well. Hey, do you have a whiteboard marker? This was under whiteboard markers in the supply closet. Uh-oh. Oh well. Everyone gets one. Yep. I will not. Oh man. Oh well. I'll be working over here from now on. And fixing that later. Well, there's... I don't know. Can I just pull down another one? So let's just get rid of that for now. Don't worry about it. Right, so we've got our struct. Got our nodes. They point to other nodes. And at some point, they'll point to null. And we need to free all of them once we're done with them. And this does erase. Perfect. So we wrote quite a bit of code last week. One of them was inserting at the head, which was good. Inserting at the tail also worked. The one bit of code that worked in some scenarios, but not all of them, was inserting at the index. This is where we inserted at a certain position in our list. Now, the problem with our insert at index is that we only considered cases that I'd refer to as expected cases, things where we sort of think the linked list will behave how we would expect. There are three types of cases in programming if you put them into really broad categories. You've got expected, you've got boundaries, and then you've got completely unexpected cases. We're not going to worry too much about the stuff we completely don't expect to happen. Like if I ask someone, give me an index for a list, what would be a reasonable answer to that question? Yeah, an integer? Yep, so like what's an integer? One? Great, good integer. Any other integers that we know? Two? That is another one, perfect. So what would be an unreasonable thing to ask to give me? Negative? What was that say? Yeah. So I like the thinking with negative. In some languages, negative integers are a thing, and I'm still not that upset if people send me a negative integer, because it's still an integer. But if someone sends me like the word hello as the integer, as the index, I'm going to be like, what are you doing? So we've dealt with our expected cases for this one, and we're not going to worry about someone sending me the word hello, but what we might want to worry about is things that are called boundary cases, or sort of a bit edge cases. And an example of that would be a negative number, because a negative number is a pretty reasonable thing to enter. We are able to pretty easily program a case where that happens. And so let's take a look. So we're inserting at an index right now. And the cool thing about doing this is we actually get to decide how we're going to deal with it. So let's say what are we going to do if the index is less than, well, what's the first index in our linked list? 0? Yep, okay, cool. What do we want to do if the index is less than 0? If someone gives me -1 and says put it there.
Print kill yourself and it's out.
I'm not going to do that one, but we could print an error message. We could just return something. In this scenario, if someone gives me a negative index, I'm just going to return the head because I'm assuming they're going to want to put it near the head or they just got confused. So I'm just going to return head. Are people happy with that as a case? Sure. Now another boundary case we didn't consider, we set counter equal to 0 because that's where we start. And then we check if counter is less than the index -1 for our while loop. And so what scenario do we not deal with when we're inserting at an index? Close. The edge case that I don't think we deal with is when they're trying to insert at the head, trying to insert at 0 itself. And so sometimes we need to program a special case, which we had to do for deleting at the index. If the index was 0, we had to do something special. And so for inserting, if the index is 0, let's do something special as well. How do we insert at the head of a linked list? What do I need to take care of? I've got my linked list. Yep. Okay, cool. So we've got the head pointer. We've got new node, which will just be somewhere in memory. This is going to point to null for now. Although it might not, it might point to some data. And this will be our new node. So what do we want to do first? You said point head to new node. So what happens if I point head to new node first? What's the problem with doing it this way? We've lost the other one. So what should we do first? Cool. So I can say new node dot next or new node arrow next. Sorry, that was a Python thing. Is equal to the head. So let's write that down. We'll go new node next. So it said new node next is equal to the head. And now what should we do? Set head to the new node. And does that look like a valid linked list to us? Yep. Awesome. Right. So we'll go new node next is head. Head equals new node. And we will return head. So let's see if that works. I'll come all the way down. I made a bunch more nodes since last time. I made up to 8 of them. And so I've just inserted them all at the tail. And so if I run the code right now, oh, cool. I've used head on line 186 without properly declaring it. Oh yeah, that's a surprise for later. Let's clear that again. We'll run our program. And right now we've just got a bunch of nodes in our linked list. It goes 11, 8, 7, 15, 20, 54, 35, and null. But what if instead of inserting 35 at the tail, I'll check insert at index, head, 8th node, and I give it index 0. Where do we expect 35 to end up now? At the head. Let's try it. and 35 is now at the head. So our code now works with that edge case. Are we happy with that? When you're doing linked lists, you always want to be thinking about, well, what happens if we need to do stuff right at the head? So if the head has to change, what happens if the linked list is empty? Or what happens, I think those are the main two ones. If the linked list is empty or if something changes at the head. So let's come back up and deal with another edge case we've not considered in both of our bits of code. What does this while loop assume? This while loop makes an assumption that's not necessarily true. And it's to do with the next line. Is anyone in chat screaming it out? Counter is initialized to 0. To what, sorry? Asking me to chmod.
Sorry, as in like the live code is live.
No, I was told it was. All right, how do I freeze the screen again?
When it's null, like if the index is too large, it'll put null.
Yeah, if the index is too large. So I'll quickly write this. The other scenario that we don't deal with is if we keep going next, checking while our counter is less than the index. But what if we keep going to the next one and the index we were given is bigger than the number of items in our linked list? That's the problem that we're dealing with. So we should also be checking something like and current is not equal to null. And this means if we give an index that's too large, we won't get an error that crashes out because we get to null in our linked list. Because let's say for this list here, how many items are here? There are 2, which means the last one is at index 1. We could insert at index 2, but if someone said they wanted to insert at index 3, then we would go, okay, well, the counter is less than 3. We'll go here. The counter is still less than 3 because we've increased it by 1. It's still less than 3. And then we'll go to null, and it will still be less than 3. So we'll try to go to null next, and it will fall to pieces. Right, I'm going to quickly chmod the code real quick. I'm going to freeze image. How do I free? You said I wanted to chmod the code, so I have to freeze this? Yeah, could you please show me how to freeze it is what I mean.
You're asking for that. Oh no, we're just not on the screen.
Oh, okay.
Yeah.
And then also actually, I don't have the command for, yes.
You're good then.
I don't have the command for chmodding either. Do you know it?
No.
Right, I can get it from Teams.
Huge.
Maybe. Right. Is it back? Are we good now? Are we so back? Yeah. All right, we'll see what happens. All right, those are the 2 main bugs I wanted to talk about in what we'd done last week. Do people understand what those bugs we're talking about? Are there any questions about what I just talked about? Please ask. All right, I'm going to take the sort of stunned silence as a yep, that was all clear. Cool. So now is where we're going to start doing some sort of LeetCode linked list problems. Because what is LeetCode? That is a great question. LeetCode is a website where you can do a bunch of small programming problems, and they're measured not only on whether or not you get them correct, but also based on the efficiency of your solution. LeetCode is sort of notorious because in job interviews, a lot of companies like to ask LeetCode type questions, and they're a bit more notorious because they'll say something like, can you please invert this binary tree recursively? And then you get the job, and they ask if you can make the button on the web page more zazzy. So it's a bit like a weird mismatch between those sorts of things, but it's meant to demonstrate your programming skills in an interview type scenario. And also they match up pretty well with what are typically asked in an exam, but please don't go and start grinding LeetCode hard problems. Those are like really for people who want to work at Google or Microsoft or other companies like that. It's just a fun word. Right, so one of them will be inserting in order. So until now, we've just been inserting based on an index. And so we've said, I want to put my data at the head, I want to put it at the tail, I want to put it at position 2. But now I want to think about, well, what if I want to insert my items in numerical order? What would be a way that I could do that? I'll have to write a new function to do that. So we've got our first node, the head, which contains the number 11. And it currently just has a pointer to null. And our second node is a node containing the number 8. And it currently also points to null. So this 11 is our head right now. And what I want to do is I want to write a function. I'll comment out all of the other ones for now. Unused, that's fine. My linked list currently goes 11 and then 8. And I want to insert them in an order so it goes 8 and then 11. So we need to figure out how we can insert our nodes in order. What sort of steps are we going to need to take to do this? These are our nodes right now. We've got the head pointing at 11 and we've got 8. How do I know, how am I going to put them in order?
You do it based on like the data inside.
Yeah. So inside each node, we can look at the data and we can check what order they appear in. So let's start with funnily enough, I've started with a bit of an edge case because we're changing what's happening at the head here, but that's fine. So let's start with checks if the head is let's check if the new node is smaller than the head. I'll go if new node data. Remember the arrow is dereferencing. How do I check if it's less than? What sign do I use? It's the less than sign. Is less than head data. Oh. What am I going to do if this is the case?
You just insert at the head.
Yep. So I could call my insert at head function with these two nodes, and that would be quite good because it allows us to reuse our code, and it's really a bad idea to be writing repetitive code over and over again. But I'm sort of imagining this as more of an exam-like scenario where we don't have our insert at head function readily available, so we'll need to write the code ourselves to do that. So what code do I write to insert at the head? Yep, so I'll do new node next is equal, yep, equal to the head. And then I'll do head is equal to that new node. And then I will return the head. And at the bottom, I'm also going to return head. And hopefully now we should be inserted in an order. I know they're unused for now.
Why not? Shouldn't you return the new node? The new node should be pointing to that head.
Yep.
Oh wait.
What happened there?
The node function.
I didn't change what I called. And now our linked list is in order. It's in order from smallest to largest. I'm going to change all of these calls down here from insert at tail to insert in order, and we'll slowly build through the rest of it. So our next node, right, so our list now looks like this. Eight now points to 11, which points to null. And our head points to 8. Our next node, called third node, is actually going to do the same thing because it's 7. And so 7, where should 7 go in this linked list? At the head. So in fact, I don't need to write any new code, I don't think. I think I can just call insert in order on the third node, and it will go straight at the head. Who thinks I'm right? Who thinks I'm wrong? Who has some sort of unknowable third opinion in this binary dilemma? All right, right or wrong, let's see what happens. Yep, cool. So, because we've written our case already to deal with inserting things directly at the head, we can have our new node. I really should have gone over there more, but oh well. That's the cool thing about linked lists. They can be anywhere in memory. In this case, memory being the whiteboard. So I can just put 7 over here, point it to 8, say that my head is over here now, and you may think that it was poor planning that caused me to draw it on the whiteboard like that, but in reality, it is a perfect metaphor for the heap itself. Never doubt me. Right, next up we have a fourth node we're going to want to insert at the head. That fourth node contains 15. Who thinks that this is going to work right off the bat now? We've programmed for inserting things directly at the front. I need to put 15 in. So we're going to be good? Are we good to go? I reckon we're good to go. We are not good to go. We will need to program this one. So let's come back up. Let's think about it. We have a node. It contains 15. It points to null. We start at 7, which is our head. How are we going to insert 15 in there? We're going to have to traverse every single node until we get to the end, and then we can make that point to 15. So let's write one of my favorite lines of code of all time, I think. I think everyone here has a favorite line of code. This one's one of mine. It's struct node star current equals head. Because whenever you do anything in a linked list, this is just so handy. It means you're not going to mess as many things up as you could. So just going to... So now I want to go until I get to the end of my list. What should my while loop condition be in that case? Nice. I'll go while current does not equal null. Who thinks this will do what we need it to do? Yes, I don't write in C often enough. Thank you. Right, so what's going to happen here while current is not null? We're going to go current equals current next. there is a issue here. What's going to happen? Is current null here? No. So current's going to be current next. Is current null here? So current's going to be current next. Is current null here? So current's going to be current next. Is current null here? Awesome. So now I want to go back and link that to my next one, but we can't. So what should my condition be instead? Yeah. Perfect. And usually it's probably just going to be one of those two conditions. I'm not going to promise it will never be anything else though. So current is equal to current next. This will take us to the end. If we get to the end of our while loop, we're at the end of our linked list. And so what can we do now that we're at the end here? We can go current next is equal to our new node. And then we can return the head. So we traversed our linked list. This is linked list traversal. We started at the head. We went to next. We went to next. Next pointed to null. And so we did not move from here. We saw that we were pointing to null. And we said, I don't want to point to null anymore. I want to point to my new node, which is 15. For my own peace of mind, I'm going to move this line down here. And so now we can insert at the head in order. We can insert at the tail in order. We will have to check the data very shortly. I think new nodes next is automatically null. So we're fine. Because when we initialize a node, its next value is set to null. So our next node after 15, I'm going to change this from 20 to like 13. So now here's where the things are going to get tricky. Because now we're going to have a node over here, 13. Where will 13 go if we're inserting in order? It's going to go between 11 and 15. So we're going to have to program a scenario where we can put 13 between 11 and 15. Let's come up and take a look at that. All right, I'll test this code first. Yep, code works. Does it work with our fifth node? What do we think is going to happen with our fifth node right now based on what we've written? Is it not going to work, or is it going to do something unexpected? All right, let's see if it doesn't work at all. It does something. It inserts 13 right at the end, but it doesn't do what we want it to do, which is insert it in order. So let's try inserting it in order. So inside this while loop, we'll need to start keeping track of some things. So what I'll probably do is I'll say, if current pointing to data is less than new node pointing to data. What should we do if the current data we're looking at is less than the data that we want to be looking at? Oh yeah, you're right. Sorry, other way around. I meant to write it the other way around. If new node's data is less than current's data. So our new node data is less than our current data. Let's see how that works. We start at 7. Is 13 less than 7? No, so we'll move on to the next one. Is 8 less than 13? Sorry, is 13 less than 8? No. Is 13 less than 11?
No.
Is 13 less than 15?
Yes.
13 is less than 15, but notice we've run into a problem again, because what I want to do is insert 13 before this, but I can't. Why can't I do that?
Because you set the 11 to go to 13.
Because I need to set the 11 to go to 13. And so there are a few ways you can go about fixing this. Some people like to use a previous node to keep track of what came before. Some people like to do this, which is where you string things together. Current next data. So we know that current next is not going to be null, because that's in our while loop. Our while loop says current next can't be null, which means we're relatively safe to say while our new node's data, if our new node's data is less than our next bit of data, which means now, when we get to 11, we're not checking if 11 is less than, we're not comparing 11 to 13. When we're at 11, we will compare 13 and 15. So if this is the case, and the node that comes after us is bigger than the node we want to insert, what should we do? Aside from we should insert it here. How can we insert it here? There's a lot of moving parts going on here.
The new node to what the current next is.
All right, set the new node to what the current next is. Yep.
Yep. And then we set the current node to 13.
Yeah, I love it. So we're going to set our new node to have its next be equal to what our current node's next is. So what's that saying? What that's saying is we're looking at 11. 11 is our current. Our new node, which is 13, will now point to 15 as well. And then we're going to say current's next. What is that going to be equal to? Our new node. So currently, current next is 11 pointing to 15. But we're changing that. What's 11 going to point to now? 13. This metaphor's gone out the window because these are really quite tricky to follow. So now we started our head with 7, which points to 8, which points to 11, which points to our newly inserted 13, which now points to 15, which then points to null. I don't know if the style guide banishes it, but I'm a big fan of once we do something like this when we're inserting, we should return now. Because what's the purpose of our function?
So like insert the node, and once it's inserted, it's finished.
Yeah, the purpose of our function is to insert the node. Our node is inserted. We've done our job. Should we keep doing things?
No.
No, my job's over. I'm going home. Let's return.
Wait, so that's good stuff, right? Because that's all
I haven't read the style guide. I'll read it one day. Let's see if this works. It's always fun to talk a big game. Oh, no. Oh, I just called it new. It's meant to be new node. New node next. And now it's inserted in order. And so I'm going to uncomment the rest of my insert in orders. And I'm relatively confident that at the end, we will end up with a list of things that are inserted in an order. Who's with me? Who's against me? You're against me? Fair enough. You can think of one error? Well, let's see if it comes up. Oh, that's a good error. Insert in order declared. Oh, because I can't spell. Is that the problem? Oh, yeah. Yep. I gave an extra 0 because it used to be insert an index. All right, my confidence has been shaken to my core. Let's try it again. And things are inserted in order. Voila. Thunderous applause breaks out. Perfect. All right, do we have any questions about the insert in order function? I think insert in order is one of the trickier things to write with linked lists. So do we have any questions about it?
Shouldn't you like check if like the head is empty?
Yep, great point. We should check if the head is empty. So let's write that real quick. In fact, I'll do that before now. I'll go checks if the head is null and if the head is null, Then I will go head equals new node, and I will return the head. Yep, so in the scenario where someone passes null in as the head, we now deal with it. Are there any other questions about insert in order? All right, we're all on side. It's now 12 o'clock, so I think it's time for a quick 5-ish minute break, and then we'll come back for a Kahoot, and then we'll do more linked list problems that are shorter than this one. All right, and thank you for being patient about all the technical difficulties at the start. I'm hoping the second half will be much smoother. I'll see you in like 5-10 minutes. All right, we've got 34 people. Can we get more than that? I got a real Pokemon card pack from the people that came to talk on Monday, so there are some pretty neat cards in here. And some like regular ones, but there's like a couple of sort of not holographic but slightly shinier than normal cards in here. So you really want to go hard in this Kahoot. I'll give another 2 minutes for anyone who wants to join. All right, we're at 47. It is week 9. I understand. People are sad. People are tired. I'm also tired, but that's a permanent thing. Dun, 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 dun. All right, we've got 49 contestants in. This is 20 fewer than last week, which means you have a higher chance of winning, statistically. All right, are we ready to go? Are we ready to roll? Ready to roll? Ready to roll? I'm ready to roll. It's time to roll. Kahoot at work. I am at work. Which of the following best describes a node in a linked list? We're testing all of your linked list knowledge. What is a node? All right, awesome. Basically, everyone got that. This is good. A node contains data and a pointer to the next node. Technically, a node could contain data and a pointer to the previous node if it were a different type of linked list, but that would have to be, how would that work? Because if you're pointing to previous and not next, then technically you're just pointing to next anyway, but you can have doubly linked lists, but we're not worried about that in COMP1511. Good job, Rocky Crane, an adorable crab. Oh, good job, everyone. These names are funny. It's a puzzle. You need to arrange things in order. Arrange the steps to insert a new node at the head of a linked list in the correct order. That's right, a new question type. We're switching things up. All right, this is the order that you do it in. First step, whenever you're doing anything on the heap, what's the first thing you need to do? You need to allocate some memory. So if we don't allocate the memory, we can't do anything. Once we have allocated the memory, we can put the data in our new node. We can't put the data in before we allocate the memory because otherwise the memory for that stuff doesn't exist. Now here's the part where I assume people got them around the wrong way. I can't actually check, I don't think. Oh well. So when we have our head, which is maybe an 8, which points to a 9, and we have our new node, which contains 15, if the first thing we do is update the head pointer, because 15 will point to null first, if the first thing we do is change head to stop pointing at 8 and to start pointing at 15, what's gone wrong here? What have we lost? We've lost the rest of the list. It's gone. We can't find it anymore because we got rid of our only way to get there. And so instead, before we update the head pointer, we must update the next pointer of this new node. It no longer points to null. It now points to 8, and only now can we move the head pointer off of 8 and to our new node. Inserting at the head is a fundamental concept of a linked list, and this is a really good exercise in pointer management, so please lock in for that one. All right, next up. It's another puzzle. We want to traverse and print a linked list in the correct order. Well, we're arranging the pieces in the correct order. All right. So again, a pretty close split. The first thing, and one of the first things you should do in any linked list exercise is make a pointer, preferably called current, and set it to be pointing at the same thing the head's pointing at. First thing, making current. It's one of my favorite lines of code for a reason. We then check. Normally using a while condition, check if current is null. We'll go while current is not null. If current's not null, we'll print out our data. And then we will take current, and it's no longer going to point here. It's going to point to the next one. And then we'll repeat the process again. We'll check if this one's null. If it's not, we'll print it. Otherwise, we'll keep going. This is traversing and printing a linked list. So the multi-select, there may be more than one answer. What ones require us to traverse down the list? Well, all right, nice. Good job, everyone. Basically, everyone got that one. So, if we're inserting at the head, we don't really need to go much beyond the head. Same with deleting from the head. Because we are at the head already, we don't need to traverse down the list. But if we want to delete at the tail, we have to get all the way down there. And if we want to search for a node with a specific value, I mean, sometimes it's at the head, but on average, we'll need to traverse down the list a bit. If you want to learn more about the averages of traversing down linked lists, I'm pretty sure data structures and algorithms will talk about one of my favorite topics. True or false, 50-50 chance of getting it wrong. Linked lists that we've learnt can only be traversed in one direction. True or false? Yeah, we're dealing with these things called singly linked lists, and this means they only point to next. And once we've gone to next, we can't go back. So you need to be certain that you've done everything you want to do at current before you go to next. There are linked lists that can be traversed in multiple directions. They're called doubly linked lists. They're a nightmare. Another multi-select. Which ones require us to malloc, which is to allocate some memory? Yeah, I think it's really mean to make a multi-select question and just have one option be the right answer, but I didn't design the Kahoot. It's not me. But yeah, the only thing here that requires us to malloc is when we're doing an insertion at a specific point, and that's not actually because we're inserting at a specific point, it's specifically because of the line new data. We're making something new, which means we need to malloc some memory for it. Which then require us to free. Yeah, once again, just the one, just deleting, and that's because once we are done with a node, so we do want to free everything we malloc, and normally we have a free function at the end that goes through the linked list and frees everything that's in there. But if we say get rid of 10, by going over it, when we go down and free everything in our linked list now, we're not going to free 10. So we've got to make sure that we free it when it's been deleted. And I think there's one more question. True or false? Linked lists require contiguous memory allocation. Things have to come one after the other. No, so I think some people who put true might have thought that they meant we have to allocate the memory repeatedly for every node, which is sort of allocating things one after the other, but the memory itself, the places in memory are not contiguous. They're all over the place. Just like my drawings on the whiteboard, one node could be here, the other one could be there, the third one could be somewhere else on the heap, and we use our pointers to link them all back together again. They don't need to be one after the other like in arrays. All right, let's see our results and let's see our winners. Let's see who's getting some cool Pokemon cards today. Right, Adorable Crab, Proud Gator, and Rocky Crane. If any of you are in class, please come get a Pokemon card. Which one were you?
Rocky Crane.
You were Rocky Crane, so you get to choose out of 3. As you should be, you've been doing great.
Sorry, can I say
Yeah,
no?
for sure.
Oh, this is a hard choice.
It is a hard choice.
I think I'm gonna go with Carablast.
Go with Carablast? Good stuff. All right, show it to the camera, please. All right, and which one of you was Proud Gator? You were Proud Gator? Right. You get to choose out of 2. Oh, can I see it? I like them. Singapore, nice. Show it to the camera as well. And so I'm going to shuffle, and you'll just pull off the top. Are you happy with that? What are you getting? What have you got? You've got unpheasant. Nice. Good job, everyone. Now that we've had fun, it's time to do linked lists again, which are also fun. Oh no. I say it's also fun, and then the next function that I've written is called reverse linked list. So, did you do it? Was it easy? All right, well, I was told it was fine even though it was in the lab. So we have our linked list, which is in order from smallest to highest. And we're going to reverse our linked list. Someone's pointed out that this was in the lab. Who here has done this function before, reversing a linked list? 3 dot, a few people. I'll give it a shot anyway. I want to see if I can reverse the linked list. What's the first thing that I always write whenever I start dealing with linked lists? Yeah. Struct node star current equals head. I'm also going to make 2 other struct node stars. I'm going to make one called struct node star previous, and I'll set that equal to null. And I'm also going to make struct node star next and set it equal to null. What sort of a while loop am I going to need here? Hey, sorry guys, can we like lock in? I'm trying to lecture here. Thank you. Thank you. All right, so we've got current, previous, and next, and we're going to use these to reverse our linked list. Our linked list, which is 1 to 7 to 8 to some other stuff. Points to 7, points to 8, points to 11, and that's probably enough for on the whiteboard. This one is our current. So we want it to end up at the end. And I've got this other pointer that I've made called prev, which currently points to null. And I've also got next, which we haven't defined yet. But what do you think I'm going to set next to? It's sort of in the name here. Well, actually, let's start with a while loop condition. What sort of while loop condition is usual for this type of problem? We're going to have to traverse down the list. What should I write? So we'll try while current next does not equal null. But in fact,
You made a next, right?
yeah, I made a next. Actually, well, I might even do, I think for this one I might try while current does not equal null and see what happens. Yeah, it is. I'm just going to call it prev because then I don't need to learn how to spell. It's a life hack for you. If you just make your variable names really short, you can't misspell them as easily. Right, so what is next going to be equal to?
Current next.
Next can be equal to current next. Nope. All right, so this now says that our next node is the one that comes after current, so that's pretty straightforward. Now we want our current, which is the first one on the list. We actually want it to point to null. So how can I make it point to null? Because it's going to end up as our last value in the list. Current next equals null. That is it. Yeah, but if I want to keep doing it further down, because I don't want the next one to point to null. I want it to point back here. So I wanted to point to something that comes before it, right? Yeah, prev. So I'll go, yep, current next equals prev. So now, current is here, next points to the 7. Oh man, this diagram's going to get disastrous. What have I done to myself? Current's next is now pointing to null. So now what do I want prev to be so that the next item that I use can point back to what current currently is? I'm going to update prev. Yep, you're right. Now, yeah, I'm going to say prev is equal to current. And now I want to move current 1 down. But current next is now null, so I can't say current equals current next. If only I'd had the foresight to put current next into a variable and save it for later.
Current next equals next.
Not quite, because current next has to be that null. Current equals next. I did save it for later. I'm a genius. And so with these lines of code, this is how you reverse a linked list. So let's prove this with the next one, because current is now equal to next. So current will come down here. And let's go through the steps again. What is next going to point to now? Next is going to point to the next one that comes after current. What is current next going to point to now? 1, which is our previous. What's prev going to point to now? Wherever current is. And where am I going to move current to? Where next is. And now we do it again. Where's next going to point to? Next is going to point to 11. Where's current going to point to? Back to prev. Where's prev going to point to? Where current is now. And where's current going to go? Where next is. And we'll do that again, but I'm not going to make us go through all the steps again. But know that it will point it back. Well, this shouldn't be here either. Do we agree that these steps are reversing the linked list for us?
Yep.
There is one slight problem, which is that at the end, because I've said while current does not equal to null, next is eventually going to point to null, and so will current. And prev is going to be pointing to our last node. And so, with these lists, with these linked list things, we're often returning the head, because that's what we want our main to have access to when we want to do other things to this linked list. What is the head now? Prev is the head. So instead of returning head like we've normally done, once we finish our loop, we're going to return prev. And I believe
Well, you error because your next would be pointing to like not null. Right?
how so?
Because you're saying that the next equals current next, right? And when current is equal to null.
Yeah, it wouldn't be in that while loop because current is null, so we won't do all of that stuff. Let's have a look. Let's see what happens. So instead of printing I'll keep printing the linked list here, but I'm also going to go head equals reverse linked list, pass in the head, and then I will print linked list and pass in the head. And hopefully, we've ended up with a reverse linked list. Right, I'm going to document this code now because it's a bit confusing. Are there any questions about reversing a linked list? What happened here? No, people seem generally happy. I'll still comment through it anyway. We're going to keep going until current is null. We are storing current next for later when we want to traverse down the list. We're setting current next to what came before it, which is null at the start. For future iterations, prev will be whatever node we were just at. And now use what we saved and move down to the next node. And here, because the head is no longer the head, we need to return prev instead. Bit of Dr. Seuss action in there for people. Right, so that is one problem. That's a sort of thinking through linked list reasonably that I would expect to come up in an exam-like scenario. Again, the caveat being, I've not seen the exam, I've not read the exam. What sort of difficulty would you put that at, out of curiosity, tutor people? Yeah, a 3 dots, so what does that mean? I guess these people know what that means, and I'll figure it out. Nice. All right, what do I want to do next? What about concatenating two linked lists? I'm going to need to make a new linked list to do this one. So I'm going to go head2 equals create node. I'm going to do these in multiples of 100. I need to define my struct. Node star head2, going to create a node. I'll make this one 4 nodes long. And in fact, I can actually just link them up here. I can just go head next equals, head2 next equals new 2, and head2 next equals new 3. I shouldn't do this, but I have too much fun doing it. And head2's next is new 4. And I'll comment out my reverse stuff, and I'll print a linked list with head2. I'm so inconsistent with my underscores. Isn't it great to know that even as someone who's been programming for years, I still forget my semicolons and misspell my variable names sometimes? Doesn't that make you feel so much better about this whole programming thing? Not really? All right, fair enough. Some people, yeah. So now we have 2 linked lists. And what I'm going to do is I'm going to concatenate them, which is a fancy word for put one after the other. And so here, I will go head equals concatenate linked list. And I'll take head1, I'll take head2, and I'm going to put them together. So I want to take, I've got my two linked lists. And I've got my second linked list. And I want to concatenate them together. So what are the steps I'm going to need to do to make this list join up with this one? And I'll say the second list goes at the end.
Wait, so we want 30 to go to 100? Or
Yep, we want 30 to point to 100.
okay.
Yeah, so we want to traverse through the first linked list and have the head point to the second one. So let's do that now. What's that bit of code that I love so much? Oh, heck yeah, it is. Struct, node, star, current. Thank you very much for saying head 1, because in every single practice that I've done of this, I wrote head instead of head 1. And I'll go while current or current next? Current next. While current next does not equal null. I'll go current equals current next. And then at the end, I'll just go current next is equal to head 2. And I will return head 1. And we're sorted. What was that, sir? Oh, did I forget a semicolon? Of course I did. I should have brought the top list down today. I forgot. I thought I'd make fewer mistakes. So let's print a linked list now. What the heck? It claims that I've probably just misspelled things. You're calling a function. It's just called concatenate, because I didn't think I'd be able to spell the rest of it. No, what have I done? Head 1 on line 265 without declaring it. Yep, because this one is just called head and not head 1. On line 266, I did the same thing. There we go. And now we end up with our two linked lists concatenated together. All right. There's a lot of headache for a relatively straightforward program, but there is one scenario that we've not considered, or technically two scenarios that we've not considered. Can you think of them? Well, yeah. Sort of, if they're both null, or more aptly to me, if either of them are null.
Yeah.
So let's think about if head 1 is null. What should I return here that will give me a linked list of some kind? I'll just return head 2. Because head, and do we care if head 2 is null here? Inside this if statement, I mean. Doesn't actually matter if head 2 is null, because head 1 is null, so if we return head 1, we're going to get null no matter what. We might as well return head 2, because it will either be null, and we'll get null either way, or it will actually be a linked list, and we'll end up with what we're after. In a similar vein, what do I do if head 2 is null? Yep, we'll do the reverse, we'll just return head 1. So I should use an elif statement. The reason it doesn't matter is because the only way I'll get into this I can't get into both if statements because of the way returns work. Returns are saying I'm going home, I'm done. And so there's no way for both these if statements to happen. But I will write an elif statement instead. Because, is it elephant C? Ah, that's so sad.
And it should be on the, like, for star, it should be on the left.
That's stylistic, but also, like, true. And so now we also deal with cases of if either head is null, we do our best to return what might be a linked list. Might not be, we might still end up with null at the end if null is passed into both of them, but if one of them is null, and there's a linked list, we will end up with a linked list. So let's document that as well. Head 2 might be a linked list, so we'll return it. How do the rules about style work if I want to comment above an elif? Because you said it has to go up here, but what if I want to put a comment here?
I don't know, actually.
You should put it inside the, like above the actual code.
Like, do you put it under as a...
Yeah.
Like in here?
Correct.
All right, fair enough.
Okay, yeah.
If head 2 is null, head 1 might be a linked list. So we'll return it. Otherwise, we'll traverse the linked list as normal until we get to the last node. And then adding head 2 to the end of the first linked list. And we only need to add that one node because that node is linked up to all of the other nodes. So we don't need to worry about adding every single node. Once we make that one link, we're done. Sophia specifically asked me to do these two because what we've not done too much of is actually dealing with the data inside the linked list. And so I will now write a function which is called, it's going to be, I'll make a counter, what's called int count of 6, set it equal to 0 for now. And then I'll go count of 6 equals, whatever my function was called, it's called div6. And I will write printf %d nodes were divisible by 6 in my linked list \n. And now I will run it. You have less arguments. Oh, right, because you need to actually pass something into your printf statement if you want to use %6. That makes sense. And tells me that 0 nodes were divisible by 6 in my linked list. Oh, perfect, we're done. Not actually, though, because 54 is divisible by 6. So there's one there. And 150 is also divisible by 6. Yeah, 120 plus 30. So we should end up with 2 at the end. So let's go through and fix that. I'm going to just start with our classic if. How many nodes are divisible by 6 if our head is null? Yeah, none. So we can just return 0. Otherwise, say it with me. What's my favorite line of code to write? Come on, energy. Yeah, struct. Perfect. We'll work on synchronicity next time. Struct node star current equals head. Please write that line of code. And we'll go while. Shall we do while current next or current itself? Current itself because we want to get all the way to the end of the linked list and check every single thing. So we'll go while current does not equal null. And we will check. How am I going to check if it's divisible by 6? I am hearing lots of good things, so I'll do if current data, And how do we check divisibility? Yeah, the percentage sign, modular arithmetic, also known as clock arithmetic. I don't know what it's like here, but there's been a really large number of students who during an exam at my previous institutes just completely forget what modular arithmetic is. We ask them to check if something's divisible by 3, and just because it's so uncommon, the percentage sign just goes out the window and they don't remember. Yeah, check if it's an even number. Just check repeatedly if it ends in a certain, that would work for 6 as well, but if mod 6, what will be the remainder when I divide by 6? 0, that's what mod is. Mod is the remainder when you divide by the number. And will I add to my count? I should make a counter. I haven't made a counter. I'll go int counter equals 0. And what should I add to my counter? Probably just 1, yeah. Counter plus plus. And then, do I want to go to the next node? Yeah, let's go to the next node. And at the end, we'll return our counter. And hopefully, this means that we now found out that 2 nodes in our linked list were divisible by 6. And we do. We've found that out. We've got 5 minutes to go, so I will do one more, hopefully short one, which is deleting something if it's divisible by 6. So we're not deleting at an index, not deleting at the head or the tail, we're deleting based on a condition. For simplicity, we'll only delete the first one that's divisible by 6. I won't get you to say it with me this time, but I'm going to go struct node star current equals head. I'm going to do the same thing as before. Well, no, I'm going to do a different thing as before. I'm going to go while current next is not null, because I want to, once I find out if it's divisible by 6, I want to remove it. And because of that, I need to do my classic trick of if current, not inside the brackets, if current next data. So I'm not checking my own data, I'm checking my next node's data. And what am I checking? Checking if mod 6 is equal to 0. If this is the case, I need to delete it from our list. And there's a few steps involved in deleting things from a list. What was that, sir? Yeah, I will actually. I'll need a, what will I call it? Struct node star, let's call it next, which is equal to current next. What was that, sorry? All right, and now I will say node struct node star node to delete is equal to current next. Style. And now I'm going to say current next. Oh God. Current next equals. I can just say current next equals current next and not worry about storing it in a variable. But for safety's sake, let's do it this way. And I will return the head. But actually, what have I forgotten to do, aside from going to the next node? What do we always do when we delete something? What do we do? We've got to free it. We've got to get rid of it. So what am I freeing here? Yeah, node to delete, I will free it. And then what should I do in my while loop? Aside from all of those if statements, what have I not actually done yet? Traverse the list. And I will return the head at the bottom. And we'll quickly see if this works. Don't need these. I'll go head equals, what did I call it? I called it delete div 6. I've not freed head 2 now. Whatever. Free all nodes head 2 just in case. Yeah, and so we started with 1, 7, 11, 13, 15, 35, 54. We ended with 1, 7, 8, 11, 13, 15, 35, and we've gotten rid of 54 because it was divisible by 6. We're at 1254, sort of a bit ironically considering the number we just deleted, and so I will be ending the lecture there. There were 2 more functions I wanted to write. Much like Sophia, I will write the code and put it on the course page if you want to look at it and study it. Otherwise, I'll hang around for a few questions, and thank you very much for coming. Jake will be back tomorrow. Thank you. I'll take it.